Lesson: Logarithmic equations. The spectacular thing about Johnny von Neumann was not his power as a mathematician, which was great, or his insight and his clarity, but his rapidity. He was very, very fast. And like the modern computer, which no longer bothers to retrieve the logarithm of 11 from its memory, but instead computes the logarithm of 11 each time it is needed, Johnny didn't bother to remember things. He computed them. You asked him a question, and if he didn't know the answer, he fought for 3 seconds and would produce and answer. Paul R. Halmos. Use U substitution to solve the following logarithmic equations. Question 1. The quantity log base 2 of x plus log base x of 8 times the quantity log base 2 of x minus 9 equals negative 24. Restrictions. The argument and base of a log must be positive. Thus, x is greater than 0. The base of a log does not equal 1. Thus, x does not equal 1. Thus, our domain can be written as open interval 0, 1 united with open interval 1, infinity. The logs here, they have different bases. So let's apply the change of base formula. Log base x of 8 is equal. Write the fraction out with log at the top and at the bottom. Then, fill out the base with the new base you want to use. Then the old argument gets transferred to the numerator as the argument, and the old base transfers to the denominator as the new argument of that log. When we perform calculations, we know log base 2 of 8 is equal to 3. So 3 over log base 2 of x. So this equation is equivalent to the quantity log base 2 of x plus 3 over log base 2 of x times the quantity log base 2 of x minus 9, which equals negative 24. Let's perform a U substitution here to help us solve the problem. Let U equal to log base 2 of x. U does not equal 0, because log base 2 of x belongs in the denominator, and we know we can't have a 0 at the denominator. Thus, our equation becomes the quantity u plus 3 over u times the quantity of u minus 9, which equals negative 24. This is a rational equation. Its domain is the set of real numbers minus the set made of 0. So let's bring to the same denominator in the first parentheses. The LCMD of this is equal to u. So let's amplify the first fraction by u. Equivalent to u squared plus 3 everything over u times the quantity u minus 9, which equals negative 24. Now let's eliminate the denominator. Multiply both sides of the equation by u, which does not equal 0. And in doing so, we obtain the quantity u squared plus 3 times the quantity u minus 9. And because of the associative property of multiplication, u multiplies only one of the two factors, namely the first, which equals negative 24u. Now let's eliminate parentheses using the distributive property of multiplication over addition. U squared times u is u cubed. U squared times negative 9 is negative 9u squared. 3 times u is 3u. And 3 times negative 9 is negative 27, which equals negative 24u. This is a cubic equation, so let's add positive 24u on both sides of the equation to get it into standard form. Equivalent to u cubed minus 9u squared plus 27u minus 27 equals 0. Let's rewrite this quadrinomial. U cubed minus 3 times u squared times 3 plus 3 times u times 3 squared minus 3 cubed equals 0, which is equivalent to, now we compress the cubic quadrinomial into a binomial cubed using the binomial cubed formula. Equivalent to u minus 3 everything cubed equals 0, which is equivalent to u1 equals u2 equals u3, which equals 3. So 3 here is a root of the polynomial with a multiplicity of 3. Now we have to substitute our u back. Thus, log base 2 of x equals 3. And by applying the definition of a log, where the argument equals the base raised to the answer, this is equivalent to x equals 2 cubed, which is equivalent to x equals 8. Now 8 belongs to our domain. Thus, our set of solutions is the set made of 8. Question 2. 9 times log base 27 of x squared minus 1 everything squared minus 18 times the log base x squared minus 1 of 27 equals negative 53. So first we should assess our restrictions. The base in the argument of a log must be positive. So our first takeaway is that x squared minus 1 should be greater than 0. The quadratic function f, where f of x equals x squared minus 1, has x-intercepts at point of coordinates negative 1, 0 and point of coordinates 1, 0. Now here's a sketch of f of x that clearly shows that f of x is greater than 0 on open interval negative infinity negative 1, as shaded, and is also positive on open interval 1 infinity. Thus, that statement is equivalent to x belongs to open interval negative infinity negative 1 united with open interval 1 infinity. The base cannot equal 1, which is equivalent to x squared minus 1 does not equal 1, which is equivalent to x squared does not equal 2, which then is equivalent to x does not equal plus or minus square root of 2. Now, we can write our domain. The domain is open interval negative infinity negative 1 united with open interval 1 infinity minus the set made of plus or minus square root of 2. Now that we have that mouthful of a domain down, let's get to solving. The two logs have different bases. Apply the interchange argument base formula. So, log base A of B equals the reciprocal of log base B of A. The base and the argument here have swapped, and we've taken the reciprocal of them. So in our case here, log base x squared minus 1 of 27 is equal to 1 over log base 27 of x squared minus 1. So now we can just rewrite our equation with that new fact. The next logical step here is to perform u substitution. Let u equal log base 27 of x squared minus 1, where u does not equal 0. So the first term, 9 log base 27 of x squared minus 1 everything squared, becomes 9u squared minus 18 over u, which equals negative 53. This is a rational equation. Its domain is the set of real numbers minus the set made of 0. Let's multiply both sides of the equation by u. We multiply, u does not equal 0, obtaining 9u cubed minus 18 equals negative 53u. This is a cubic equation, and to get it into standard form, let's add positive 53u on both sides of the equation, which is equivalent to 9u cubed plus 53u minus 18 equals 0. So to solve this cubic equation, we will use the rational root theorem and synthetic division. So to find the roots that we can test in synthetic division, we put the factors of the first coefficient, 9, at the denominator. So those factors are 1, 3, and 9. Now at the numerator, we put factors of the last coefficient, which is 18, negative 18 for that matter, which are 1, 2, 3, 6, 9, and 18. Now, the possible zeros are 1, 2, 3, 6, 9, and 18, as well as the potential fractions, 1/3, 2/3, 1/9, and 2/9. The reason why I didn't go through and test the rest of them is actually, if you were to sit here and do them out, you would see that they all simplify to the ones I've just described. So, as a shot, let's try 1/3 as a root of the equation. Place the possible root outside the table, 1/3, and place the coefficients of the polynomial at the top. The first coefficient of the polynomial is 9. There is no second degree term, no u squared, so we have a fat 0. Third coefficient, 53. And the fourth coefficient, negative 18. Bring down the first coefficient, 9. Multiply across, so 1/3 times 9, which is 3. And add diagonally to 0, which results in 3. Now just do it again. 1/3 times 3, multiplying across, which is 1. Add it to 53. We add diagonally, gives us an answer of 54. Now repeat that process one more time. Multiply across, 1/3 times 54. 18. 18 plus negative 18 as we add diagonally is 0. The remainder is 0, Thus, the first root is u1 equals 1/3. To find the other two roots, we must solve the equation. 9u squared plus 3u plus 54 equals 0, because that was the quotient from our synthetic division. Divide both sides of the equation by 3, which we get an equivalent 3u squared plus u plus 18 equals 0. And to solve this quadratic equation, we can use the ABC discriminant formula. A is 3, B is 1, C is 18. Now, delta is b squared minus 4ac, which is 1 minus 4 times 3 times 18, which, as you notice, is less than 0, which means u2 and 3 are not real. They're imaginary. That discriminant, negative, imaginary solutions. So let's go and work with our one real solution, u equals 1/3. Substitute back in our u substitution. Thus, log base 27 of x squared minus 1 equals 1/3 by applying the definition of a log. The argument, x squared minus 1, equals the base, 27, raised to the answer, 1/3. Now, that leaves us with the equivalence statement, x squared minus 1 equals 3, which is equivalent to x squared equals 4. Thus, we get the equivalent x12 equals plus or minus 2. Now, both these solutions belong to our domain. Thus, the set of solutions is the set made up of plus or minus 2. Question 3. Log base 3 of x minus 1/2, everything squared, plus log base 3 of 9 over log base x of 3 equals 3 times log base 3 of x squared minus 23 over 4. Let's assess our restrictions. The argument and the base of a log must be positive. X must be greater than 0. The base of a log can also not equal 1. Thus, x does not equal 1. So we have our domain, open interval 0, 1, united with open interval 1, infinity. The first thing we want to do here is evaluate log base 3 of 9 to get it out of the way, since it's super simple. It's equal to 2, because 3 squared is equal to 9. Then we want to use the argument base interchange formula. 2 over log base x of 3 is equal to 2 log base 3 of x. How did this happen, you might ask? Well, by interchanging the argument in the base, we got the reciprocal. And by getting the reciprocal, we took the 1 over log base x of 3, and it became a log base 3 of x. Wonderful. Thus, we have the quantity log base 3 of x minus 1/2, everything squared, plus 2 log base 3 of x equals 3 log base 3 of x squared minus 23 over 4. Our next step is to apply the Page-pull, the power, argument, jumping property of a log, where log base 3 of x squared equals 2 log base 3 of x, since we're dropping the squared in front of our log. In doing so, we've turned 3 log base 3 of x squared into 6 log base 3 of x. Now that we have that out of the way, let's use u substitution. So let u equal log base 3 of x. Thus, the quantity u minus 1/2 everything squared plus 2u equals 6u minus 23 over 4. Let's expand the binomial squared into a trinomial using the binomial square formula. U squared minus u plus 1/4 minus 4u. That happened by adding negative 6u and positive 23 over 4 on both sides of the equation. So we get plus 23 over 4 equals 0. Our next step is to group like terms. We have a negative u and a negative 4u, which results in u squared minus 5u, and then we group positive 1/4 and positive 23 over 4, which results in 24 over 4 reduces to positive 6, which equals 0. Now this is a trinomial, and we can factor it using the guess and check technique. Equivalent to u minus 2 times u minus 3 equals 0. Utilizing the zero product property, u1 equals 2, u2 equals 3. From u1, thus log base 3 of x equals 2, and using the definition of a log, thus x equals 3 squared, thus x1 equals 9, which belongs to our domain. u2 equals 3, thus log base 3 of x equals 3, base raised to the answer equals the argument, thus x equals 3 cubed. Thus x squared equals 27, which also belongs to our domain. Thus, our set of solutions is the set made up of 9 and 27. Question 4. True or false? The equation below is an identity. 4 times common log of 3x plus 1 squared equals the quantity log of 9x cubed minus 3x squared minus 5x minus 1 minus common log of x minus 1, everything squared, for all x belongs to open interval 1, infinity. The right side of this equation has a difference of 2 logs inside the brackets. Compress the difference of these 2 logs into 1 log by applying the quotient argument property of a log. Equivalent to 4 times the common log of 3x plus 1 everything squared equals the quantity, the common log of 9x cubed minus 3x squared minus 5x minus 1 over x minus 1 everything squared. The sum of the coefficients of the polynomial in the numerator is 9 minus 3 minus 5 minus 1, or 0. Thus, 1 is a root of the numerator, which means x minus 1 is a factor of the numerator. We'll perform synthetic division to find the other factor. So we place the root outside the table, which is 1, and then we place the coefficients of the polynomial in standard form at the top. 9, -3, -5, and -1. Now, let's bring the first coefficient down, bring that 9 down, multiply across. 1 times 9 is 9, and add diagonally to that -3, which 9 plus -3 is 6. Perform that again. Multiply across. 1 times 6, which is 6. Add diagonally, add -5, 1. Wonderful. One more time. Multiply across. 1 times 1 plus -1 is 0. Wonderful. Now the remainder is 0. And the other factor is 9x squared plus 6x plus 1. The numerator factors as the quantity x minus 1 times the quantity 9x squared plus 6x plus 1. We can reduce the fraction by the GCF, which is x minus 1, and compress the trinomial into a binomial square. Thus we have the equivalent statement for log squared of 3x plus 1 equals the quantity common log of 3x plus 1 everything squared again, which is equivalent to 4 times the common log of 3x plus 1 everything squared. And then we apply the Page pull. Drop that 2 in the front. So we have the quantity 2 log of 3x plus 1 everything squared. A product raised to a power raises each factor to that power. So in this case, we get the equivalent statement 4 times the common log of 3x plus 1 squared equals 4 times the common log of 3x plus 1 squared. This is true for all x that belongs to the open interval 1, infinity. Thus, this is an identity. True. Question 5. True or false? The two equations below are equivalent. Natural log of 3x cubed minus 8x plus 2 equals 3 times the natural log of x plus the natural log of 3. The second equation, 2 times log base 1/2 of x everything squared minus 5 times log base 1/2 of x plus 2 equals 0. Let's work with the first equation. First equation equivalent to what we just read it as, but one quick step we did here, we pulled up the 3. The right side of the equation is a sum of 2 logs. Compress the sum into 1 log. Now, how do we do that? We apply the product argument property of a log, equivalent to ln of 3x cubed minus 8x plus 2 equals ln of 3x cubed. The natural log is a one-to-one function. The function can be removed without losing any solutions. Thus, 3x cubed minus 8x plus 2 equals 3x cubed. Let's cancel our like terms. We cancel those 3x cubes out, and we obtain the equivalent statement negative 8x plus 2 equals 0, which is equivalent to negative 8x equals negative 2, which is equivalent to x equals 0.25. we didn't write restrictions for the first equation. The answer of the transformed equation is a solution for the first equation if and only if the arguments are positive. Let's plug 0.25 in the argument and verify that it is positive. So 3 times 0.25 cubed minus 8 times 0.25 plus 2. This evaluates to 3 times 0.25 cubed minus 2 plus 2, which equals 3 times 0.25 cubed, which is greater than 0. Thus, the set of solutions for the first equation is equal to the set made of 0.25. To solve the second equation, we are going to use u substitution. Let u equal log base 1/2 of x, such as the second equation is equivalent to 2u squared minus 5u plus 2 equals 0. Let's use the break and group method to solve the quadratic equation. Equivalent to 2u squared minus 4u minus u plus 2 equals 0. Equivalent to 2u times the quantity u minus 2 minus the quantity u minus 2 equals 0, which is equivalent to the quantity u minus 2 times the quantity 2u minus 1 equaling 0, which is equivalent to, using the zero product property, u1 equals 2 and u2 equals 1/2. Case 1, log base 1/2 of x equals 2. Applying the definition of a log, 1/2 raised to the second power equals x, which equals 1/4. 1/4 is greater than 0, so our arguments are greater than 0. Thus, x1 is equal to 0.25. Now, log base 1/2 of x equals 1/2. Thus, x equals 1/2 raised to the power 1/2, which is greater than 0. x2 equals the square root of 0.5. The second equation has two solutions, while the first equation has only one. Thus, the equations are not equivalent. This statement is false. Question 6. Always, sometimes, or never. If natural log of x minus y over 3 equals 1/2 times the quantity natural log of x plus natural log of y, then the ratio of x to y is an irrational number. So the equation we have here is a logarithmic equation with two variables. It could have no solutions, a finite number of solutions, or infinitely many solutions. If the equation has solutions, then the ratio of x to y could be always, sometimes, or never an irrational number. Let's transform the equation. Multiply both sides of the equation by 2. Equivalent to 2 times the natural log of x minus y over 3 equals natural log of x plus natural log of y. The left side of the equation is a product between a constant and a log. So we can apply the Page-Pull, the power argument jumping property of a log. 2 jumps to the top of the argument and becomes the power of the argument. Thus, ln of x minus y over 3, everything squared. And then our right side of the equation is a sum of two logs. Compress the sum into a log by using the product argument property. So we have our left-hand side equals natural log of xy. Let f, where f of x, equals natural log of x. Thus, f of x minus y over 3, everything squared, equals f of xy. F is a one-to-one function, because natural log is a one-to-one function. So we can remove f without losing any solutions. Thus, x minus y, everything over 3, everything squared, equals x times y. A quotient raised to a power, raise the numerator to the second power, and raise the denominator to the second power. So we have x minus y, everything squared, over 3 squared, which equals 9. Which equals x times y. Multiply both sides of the equation by 9, and expand the binomial square into a trinomial using the binomial square formula. Equivalent to x squared minus 2xy plus y squared equals 9 times x times y. This is a quadratic homogeneous equation with two variables. Add negative 9xy on both sides of the equation. Equivalent to x squared minus 11xy plus y squared equals 0. Y is the argument of a log, thus y is greater than 0. We can divide both sides of the equation by y squared, which does not equal 0. Thus, x over y, everything squared, minus 11 times x over y plus 1 equals 0. Utilizing u substitution, where we let u be equal to x over y, thus u squared minus 11u plus 1 equals 0. This is a quadratic equation with one variable. Let's use the ABCD discriminant formula to solve it. A is equal to 1, B is equal to negative 11, and C is equal to 1. Thus, delta, which is equal to b squared minus 4ac, equals negative 11 squared minus 4 times 1 times another 1, which equals 121 minus 4, which equals 117. The discriminant is not a perfect square. Thus, u1 and 2 are irrational numbers. Therefore, the ratio of x to y is an irrational number because u represented that ratio. Thus, the statement is always true. Important. The restrictions of the equation are x greater than 0, y greater than 0, and x greater than y. Therefore, x over y is greater than 1. Thus, u is greater than 1. Indeed, when we solve for u1 and u2, we get 11 plus or minus square root of 117, everything over 2. The root that is greater than 1 is 11 plus square root of 117 over 2. The ratio x to y is equal to 11 plus the square root of 117 over 2, which belongs to the set of real numbers minus the set of rational numbers. Extension. We have shown that the ratio is always irrational, and that it is always a constant, which means that the variables x and y are directly proportional. Question 7. Which of the following is not a strategy that is often used to solve logarithmic equations? A. Express the equation in exponential form and solve the resulting exponential equation. B. Simplify the expressions in the equation by using the laws of logarithms. C. Represent the sums or differences of logs as single logarithms. D. Transform the logarithmic equation into a polynomial or rational equation using U substitution. E. Square all logarithmic expressions and solve the resulting quadratic equation. Or F. All of the above. G. None of the above. The answer is E. Square all terms of an equation is a technique that is never used in any type of equation. We square both sides of a square root equation to eliminate the square roots, but not terms of an equation. Thus, E is not a strategy that is used to solve a logarithmic equation. The correct answer must be E or F, all of the above. The correct answer cannot be G. D is a strategy that we've used several times in this lecture. We've used U substitution in almost all the problems we've seen today. Thus, D is a strategy that is often used to solve logarithmic equations. Thus, F is not the correct answer. It can't be all of the above if D is a strategy. The correct answer is E. The end.